Good morning, everyone. I am delighted to welcome you all today. Today, we will be exploring the fascinating topic of calibration of gas chromatography, or GC. My name is Dr. S.K. Singh, and I hold a PhD in this field. In this presentation, we will cover the fundamental principles of GC calibration, its importance, and the methods used to ensure accurate results. We'll also look at practical examples and troubleshooting tips. I look forward to sharing this knowledge with you and hope it will be both informative and engaging. Let's get started. Let's take a closer look at the key components of the gas chromatograph that require calibration. First, we have the carrier gas flow controller, which is essential for maintaining a consistent flow of gas through the system. Then, there's the injector, which can operate in split or splitless mode, and it's crucial for introducing the sample accurately. The column oven temperature needs to be precisely controlled because it directly affects separation quality. Next, we have the detector, which could be FID, TCD, or ECD, and its response must be calibrated to ensure accurate detection of analytes. We also need to focus on retention time and area reproducibility, as these are critical for consistent results. Calibration frequency is another vital aspect. Initial qualification should be done before starting regular analysis, and then calibration should be performed every 6 months or as outlined in the SOP. Additionally, calibration is necessary after any major maintenance or repair, or whenever the system's suitability fails. The overall objective here is to ensure that our gas chromatograph produces results that are accurate, precise, linear, and reproducible, all while complying with USB, ICH, and GMP standards. Remember, these calibrations are not just routine, they're fundamental to maintaining the integrity of our analytical data. Let's take a closer look at some key regulatory references that guide our analytical and validation practices. First, USB 1058 focuses on analytical instrument qualification, or AIQ, which is all about ensuring our instruments perform consistently and reliably. Next, USB 621 covers chromatography, emphasizing the importance of proper method development and validation in separation techniques. Then, we have USB 1225, which deals with the validation of compendial procedures, ensuring our methods meet the necessary standards for accuracy and reproducibility. Moving on, ICH Q2, R1 provides guidelines on parameters like accuracy, precision, and linearity, which are critical for validating analytical methods across different stages. Finally, 21 CFR 211, 160, B4 addresses the calibration of instruments, reminding us that proper calibration is essential for maintaining data integrity and compliance. Altogether, these references form the backbone of our quality assurance framework, helping us ensure our processes are both effective and compliant with regulatory expectations. Let's talk about carrier gas flow rate calibration. This is a crucial step in ensuring our gas chromatography system is working accurately. Essentially, we're verifying that the flow rate of the carrier gas, whether it's helium, nitrogen, or hydrogen, is at the correct level. This matters because the flow rate directly impacts the separation and analysis of our samples. If it's too high or too low, our results can be skewed or inconsistent. During calibration, we typically use a bubble meter or a bubble flow meter to measure the actual flow rate. This allows us to compare it against the set or desired flow rate and make adjustments as needed. Proper calibration ensures our data is reliable and reproducible, which ties back to our overall goal of obtaining high-quality, accurate analytical results. It might seem like a small detail, but it's a key part of maintaining the integrity of our entire analytical process. Let's talk about injector precision, specifically focusing on repeatability. The main idea here is to ensure that our injection process is consistent each time we perform it. To do this, we follow a procedure where we inject the standard solution 6 times in a row. After each injection, we record the peak area, which tells us how much of the analyte was detected. The key point is that by doing this multiple times, we can assess how reproducible our injections are. This consistency is crucial because it directly affects the accuracy and reliability of our results. If the peak areas are very similar across all 6 injections, we can be confident that our injector is performing reliably. On the other hand, if there's a lot of variation, it indicates that we might need to troubleshoot or refine our method to improve repeatability. Overall, this step helps us ensure that our analytical process produces dependable data, which is essential for making sound, scientific conclusions. Now, let's talk about standard preparation. When setting up calibration levels, it's common to use substances like methanol or N-hexane. These serve as our reference points to ensure everything is working correctly. Next, we focus on detector linearity calibration. This step is crucial because we want to confirm that our detector's response is proportional to the concentration of the analyte across the entire range we're interested in. By preparing these calibration standards properly, we can accurately assess the detector's linearity. This means if we double the concentration, the response should also double, which is fundamental for reliable quantitative analysis. Connecting this to the overall theme, proper standard preparation and linearity calibration underpin the accuracy and reliability of our entire analytical process. They ensure that our measurements are consistent and trustworthy, laying a solid foundation for meaningful results. The coefficient of determination, or R2, is a key indicator of how well our data fits a linear model. It helps us assess the goodness of fit for our calibration curve. When the R2 value is at or above 0.999, we consider the detector response to be linear, meaning it responds proportionally to the analyte concentration. The acceptance criterion for linearity is straightforward. R2 should be greater than or equal to 0.999. Achieving this indicates that our detector response is reliable across the tested range. Now, the principle behind this is to prepare multiple standard concentrations that span the entire working range of our method. We then inject each of these standards into the gas chromatography system. This process allows us to generate a calibration curve by plotting the peak areas against known concentrations. The main purpose here is to demonstrate that, in gas chromatography, the correlation coefficient, either R or R2, shows that the detector response is directly proportional to the analyte concentration over the specified range. This is a fundamental requirement according to USP 621, USP 1225, and ICH Q2, R1. In essence, establishing this linearity ensures that our method can accurately quantify analytes within the specified range, providing confidence in the reliability of our results. Let's take a closer look at this example data and regression for the GC linearity, specifically focusing on the FID detector. As you can see here, we're examining the correlation coefficient, which is a key indicator of how well our data fits a linear model. This is part of our ongoing discussion about assessing the linearity of our chromatography method. In this slide, we're continuing from the previous one, emphasizing that a high correlation coefficient signifies good linearity. This means that our detector response is proportional to the concentration over the tested range. Remember, maintaining this linearity is crucial for accurate quantification. By analyzing these data points and the regression line, we can determine the reliability of our method across different concentrations. When the correlation coefficient approaches 1, it indicates a very strong linear relationship. Ultimately, this example illustrates how we validate our system's performance and ensure consistent, accurate results in our analyses. Keeping an eye on the correlation coefficient helps us confirm that our method remains robust and reliable throughout our testing. Let's continue our discussion on the correlation coefficient and linearity. On this slide, we're focusing on the ongoing aspects of correlation, emphasizing that understanding the strength and direction of a relationship is crucial. The correlation coefficient helps us measure how closely two variables are related in a linear fashion. Remember, a value close to +1 indicates a strong positive linear relationship, while a value near -1 suggests a strong negative linear relationship. Values around 0 imply little to no linear association. It's important to note that the correlation coefficient mainly captures linear relationships. So, if the relationship between variables is nonlinear, this measure might not fully represent the connection. This is why visualizing data with scatter plots is so valuable. It helps us see whether the relationship is truly linear or not. In the context of our overall theme, understanding correlation and linearity is fundamental because it underpins many statistical analyses. Recognizing the degree and nature of relationships between variables allows us to make more informed decisions and interpret data more accurately. Let's take a closer look at the calculation for our retention time precision. The mean retention time, or RT, is 5.115 minutes. This value represents the average time it takes for our standard solution to pass through the system during multiple injections. The RSD, or relative standard deviation, is 0.23%. This is a crucial number because it tells us how consistent our retention times are. A lower RSD indicates more reliable and reproducible results, which is what we aim for in quality control. Now, according to our acceptance criteria, the RSD should be less than or equal to 1%. Since our RSD is well below that threshold, we can confidently say that our retention time precision is acceptable, so we pass this test. Let's also review the procedure we followed to ensure this consistency. We injected the standard solution 6 times, recording the retention time each time. This repetition helps us assess the precision of our method. By doing this, we verify that our analytical process is stable and reliable, which is critical for ensuring the quality and accuracy of our results throughout the overall testing process. Oven temperature accuracy is a critical factor in ensuring consistent and high-quality cooking or baking results. When your oven's temperature is accurate, you can trust that the heat inside matches the setting on the dial or digital readout. This accuracy is essential because even small deviations can affect the texture, taste, and appearance of your food. For example, if your oven runs a few degrees hotter or cooler than what you think, it can lead to undercooked or overcooked dishes. Throughout this presentation, we've emphasized the importance of precise temperature control, and this slide highlights why maintaining oven temperature accuracy is a key part of that. When you regularly check and calibrate your oven, you're making sure it performs reliably, which ultimately supports better culinary results and efficiency in your kitchen. Now, let's talk about system suitability, which is covered in USP 621. This step is essential to ensure our analytical system is performing properly before we proceed with sample analysis. We evaluate several parameters to confirm this. First, the percent RSD, or relative standard deviation, of the peak area should be less than or equal to 2%. This tells us that our system's measurements are consistent and reliable. Next, we check the retention time consistency. It's important that the analytes retain at roughly the same time across multiple injections, indicating stable and reproducible chromatography. If our method involves separation, we also look at resolution. Adequate resolution ensures that peaks are well separated and clearly distinguishable, which is crucial for accurate identification and quantification. Lastly, we assess the tailing factor, which should be less than or equal to 2. A lower tailing factor indicates symmetric peaks, reflecting good column performance and method robustness. Remember, the key point here is that the system must pass all these criteria before we analyze any samples. This step helps us maintain data integrity and confidence in our results throughout the entire process. Let's now focus on documentation and data integrity, which are crucial for ensuring reliable and compliant analytical results. First, having an approved calibration protocol is essential. It provides a clear, standardized process that everyone follows, ensuring consistency and traceability. Next, raw chromatograms serve as the foundational data. Preserving these original files is key to maintaining data integrity. When we look at calculations and graphs, it's important that they are accurately derived from the raw data and properly documented to support transparency. Calibration labels and due dates, help us track the calibration status and ensure equipment is maintained and accurate over time. Finally, reviewer approval is a critical step. Having an independent review confirms that all data and documentation meet quality standards and regulatory requirements. Remember, following ALCOA Plus principles: attributable, legible, contemporaneous, original, accurate, plus complete, consistent, and enduring. These points help us uphold the integrity and trustworthiness of our data throughout the analytical process. And finally, on this last slide, we come to the conclusion. Here, I want to emphasize that GC calibration is truly the cornerstone of reliable chromatographic performance. When your GC is properly calibrated, you can trust that the results you get are consistent and accurate. This is essential not only for day-to-day analysis, but also for meeting regulatory standards like those set by the USB and GMP. Compliance with these guidelines ensures that your pharmaceutical analyses are valid and credible. Furthermore, accurate quantitative results are only possible when your instrument is calibrated correctly. Without proper calibration, your data could be misleading or unreliable, which is unacceptable in a pharmaceutical context. So, to connect everything we've discussed throughout this presentation, a calibrated GC isn't just a good practice. It's a mandatory step to ensure your analyses are valid, compliant, and trustworthy. Remember, a well-calibrated instrument is the foundation of high-quality pharmaceutical analysis. For further support, please feel free to contact us. We're here to help you with any questions or additional information you might need. Remember, your success is our priority, so don't hesitate to reach out. Thank you very much for your time and attention today. We appreciate your engagement and look forward to supporting you in your journey.